think it's time to start today's discussion. Just a reminder that we're going to have our, hello. Okay, so just a reminder that we're going to, please quiet down. Hello. Okay, so just a reminder that we're going to have our first quiz, which will be scheduled on Thursday, starting 11:30. So just remember that you need to come by for quizzes, and we're going to cover mostly chapter 2. So we'll also upload some 2 examples, just to let you know what kind of question will be similar questions, examples, okay? So as I said, there will be 5 single choice questions and 5 multiple choice questions. So remember, okay, so what we're going to do today is wrapping up chapter 2, of course. So basically there's 2 more topics I want to, 3 more topics we need to address. First of all is we have already starting the discussion of reverse bias PN junction. And we know that essentially in a reverse bias junction, you essentially have something, a current which is essentially 0. Almost 0. You see some leakage. You're gonna, if you're into advanced discussions or advanced device courses, we'll talk about what kind of mechanism that causes leakage. But in our cases, we're just assuming that it's essentially 0 in the model that we're going to use later for circuits. But then what happened is that the key, I should emphasize once again, what's the purpose of a diode? If you look at the diode model, we're going to introduce a little bit, is that when you forward biasing, you want it to be conducting. When it's reverse biasing, you want it to be off, meaning that it's supposed to be in an, we call it an off mode. So when you turn off a switch, what you expect is that it's supposed to be off all the time. But it will then sustain something called a breakdown. There will be a maximum amount of, I should say, stress or level that it can endure. So if there is a breakdown characteristic. We're going to talk a little bit on that, and some of the devices actually are functioning based on its breakdown characteristics. So we're going to talk about that a little bit. And the next thing, of course, we're going to talk about forward bias. So you heighten the barrier when reverse bias. The barrier increases. We know that you increase the barrier. In the other direction is that in forward bias, we expect the barriers to reduce. So what happens is that when you reduce the barrier, you're assuming that you would then have significant diffusion current, which will be much, much larger than the drift force, because I'm reducing the barrier. So then you then allow a certain amount of current, which would then substantially amount of, I should say, let me use this. You're assuming that there will be a substantial amount of current. So if I'm defining this as my diode current, then what happens is that you would then see a substantial amount of current. So we're going to talk about what this depends on. So the next thing is, of course, if there's current, you wanted to know when I apply a certain bias, what is the corresponding response? That's called the diode current characteristic. How do you characterize that based on our basic understanding of device physics, our very limited introduction on device physics? How do you derive the current voltage equation? So once we have this current voltage relation, we're going to enter the third part. I typically refer this to as the bridging between devices and circuits. If you're a circuit designer, what you do is typically is that you construct a architecture and insert these devices into these architecture and expect what the ultimate circuit performance will look like. So in the bridging of these two is that if I insert this device, how would you know, other than these linear passive components, we already have equations describing them. We also need to construct equations describing the diode. So we call it diode model. The bridging between circuits and devices are based on device models. So anytime you do SPICE simulations, or if you're ever in the future you ever had the experience of taping out your own circuit, meaning that you want to draw your circuit, design your circuit, you run simulation. The key important thing is you need device model. So we're going to build the first device model that's going to be used in the follow-up circuit analysis. So we're going to talk about different ways of constructing these models and the reason why you want to use, there's various ways of modeling a element. Why do we need these various levels of modeling? And in terms of analysis for circuit at different levels. I'm going to talk about that a little bit. Okay? So as a review, I'm just going to briefly talk about what the key important parameter, which we'd already talked about. I like to plot electric field and voltages along the junction. So if we have a PN junction, so we already know that for white, let me use yellow. Okay, so for yellow, it's the standard. So we already constructed that for a condition during equilibrium state. So this is equilibrium. At yellow is equilibrium. As under equilibrium, what happened is that you would then build there will be a self-built-in electric field, which would then create we call it built-in potential. I think this should be Vx. And then the height of this built-in, the potential height, the barrier is VO. Okay, for the same plot, you can also do when there's reverse bias. We already tell you that if it's under reverse where VD, let me just, so this is N, this is P. So there'll be a depletion region. Okay? So if I'm reverse bias, meaning that VD is smaller than 1, here I'm defining VD as positive on the N side, negative on the P side. Right? We know that during reverse, you're essentially having zero current. ID is approximately 0. There's no current flowing. What happened is that you would then raise your potential. So the potential will be VD equals to minus VR. So what happened is that you would then, there's two ways of expressing this. You would then see a heighten of potential. This is EX for under reverse bias. And then you will heighten your barrier. So your barrier profile will look something like this. So the consequences is that you would then extend your barrier. You extend, so this is the depletion width, right? And my depletion width widens as voltage increases. So the depletion width widens. We already said that. So what happened is that the corresponding one, the first observation is that you have widened this depletion, and then we have VD. The barrier will be, I should write it down here. Your barrier height, the height of barrier will become VO. You add on VR, or the other way to write this is VO minus VD, right? You're always adding, but it's because this is a negative number, therefore you heighten this level, okay? So what happened is that we know that you could basically view it as a parallel plate capacitance. If we look at the small signal behavior, it will be something similar to parallel plate capacitance, where Cj equals to Cj0 1 plus VR. Okay? So that simply means that if I'm applying a reverse bias voltage let's say 3 times as high as VO. For example, if VO is 0.7, I'm applying 2.1 volt, minus 2.1 volt. I would then reduce my capacitance by 2-fold. Okay, so if this is 3 times, you would then expect your voltage to drop by 2-fold. Okay, so you can do simple calculation to get a sense of how this changes the parallel plate capacitance. How does the capacitance changes because it widens. The basic idea is that to have observation is that if VR increases, what happens is our depletion width, this is xn plus xp, both sides increases, the sum increases. Therefore, based on parallel plate capacitance, your distance between charge increases that will lead to your junction capacitance and decrease. So this is the basic sense you need to observe. Okay? So what happened is that we want to address one of the key things is the breakdown characteristic. So I'm just going to talk about this in a very short sense of discussing this is that under reverse bias, let's say if you measure a diode by applying a diode voltage and looking at its reverse bias characteristic, what would you expect? You expect that it will look something like this. It will look something like this. It will be almost zero current. I already said that because there's no diffusion. You inhibit diffusion by creating a large barrier, but there's no carrier even with this large electric field. So what happened is that if you apply this voltage to a fairly high level, you actually see something like this. This is typically referred to as, we call this a breakdown. The characteristic is called a breakdown. A breakdown characteristic, and this particular, what your concern is that when does this happen? What is the maximum voltage it can endure to still be shutting off? So what your concern is not, if you're not actually operating in the breakdown mode, there are some devices that are operating in the breakdown mode, but in typical operation of a diode, what you basically want is that when it's turned off, it's turned off. You don't want it to be on any time. So you want to know the base. So our key parameter in this region is of course we call the breakdown voltage. Okay. So your breakdown voltage, if you think about it, is this voltage is VR. So it's VO, so VBD. What happened at VBD is that your VBD is your breakdown voltage plus VO will then give you the maximum triangle area. So what limits maximum triangle? Let's just draw so we know that this voltage is sustained by the triangle area. So triangle area will then be 1/2. The height is E max times X. I'm just going to use W depletion. Okay, the width. So what determines your breakdown voltage is essentially 1/2 E max W depletion minus your already built-in potential. Okay? So what limits your upper, what's the upper ceiling of this, the breakdown, the limitation, what causes breakdown is actually the maximum voltage that can be sustained. So what happened is Emax is limited, I should say, each material will have a maximum that can be endured is typically referred to as the critical field. If you look at material table, it will tell you that its maximum endurable electric field inside this material is there's a limit on that. And the basic mechanism is called, there's actually two mechanisms. We're going to, the E max is limited by what we call the avalanche. I'm sure, avalanche breakdown. So anyone know what the avalanche means? Just want to make sure that I spell it right. Did I? Yeah, there's a N missing. Did I? Just sure. There's another N at the end. I'm not sure I spell it right, but some words like that. Avalanche. Is it two N's or one N? Does anyone know? You can look it up. What does it mean? Did I spell it right? Is it two N? Yes. Is it two N's? 所以我第一次听的。L-A-N 哦，这样子吗？ Let me just make it right. Is it right? Bad at spelling now. Okay, so does everyone hear what this means? 雪崩 it means that avalanche breakdown means that you've seen the movie when avalanche happens. It's like it's overloaded with snow, and then someone make a disturbance, maybe shouting. And then there's a seed of snow that rolled up and then make it all fall down. So avalanche breakdown is a sequence of multiplication. We call it when inside the junction. So what happens is that when your electric field, so the basic idea is that if I have an electron, it's moving in this large electric field. So this maximum is if this field is higher than critical field. So what happened is that this electron would then gain energy, because before, remember, the maximum amount of energy is earned is by before, I should say, in between mean free time. So in between the collision, it would then gain enough energy. So the energy gain, these electrons will gain kinetic energy. So let's say in the beginning, I already mentioned that depletion approximation tell us that there's supposed to be no electrons inside this depletion region. But during the avalanche, you assume that there's very rare cases of generation. There'll still be generation, even though the density is very low. So if you're operating in this region, what happens is that you would then have generated electrons, and these electrons will then just pass this drift region. But because the density is very low, therefore you essentially see no current. You don't actually see the amount. But during the avalanche, when the critical field built up, what happened is that these electrons gain kinetic energy. And this kinetic energy, if this energy, EK, is larger than so let's say if the field is high enough, so these electrons gain enough energy to break, what does this mean? When the energy exceeds band gap, meaning that it has enough energy to break covalence bound. So once it breaks covalence bound, it will then generate an electron hole pair. And these electrons will go back to gain kinetic energy, and then it'll become a positive loop. So what happens is that it will then form a condition that's favor a positive loop. Anytime you have a positive feedback, meaning that it will explode, right? So it explodes, then that's why your avalanche breakdown will occur. So it's a circle of mechanism that will initiate by one electron, it will then generate two will generate will generate more, and then it will continue to generate multiply. We call it multiplication. So once you have a multiplication, you'll have a positive feedback, which is with a gain of larger than 1, that means that eventually it will blow up, and then you'll see this breakdown. Okay? However, in these breakdowns, even though it's called breakdown, it will not cause, we call it damage. It will not cause physical damage. It will just allow the current to flow. So you will see this current, but if I'm reversing it back to a lower voltage, it will then go back to a lower level. If you're not damage other part of the circuit, the breakdown itself is actually reversible. Okay? The other things you typically hear is called the Zener. I'm not going to talk about this too much. This is a different mechanism. If you're interested in come to classes like solid state devices, we'll talk about the band structure, which will lead to Zener breakdown. So typically, Zener breakdown will be, this will be a much, I should say, it's heavily doped. It's unique to heavily doped PN junction. So if you see circuit symbol like this, this is typically referred to as a Zener diode. Okay? And it will actually break down at a lower voltage. The Zener diode typically have low VBD. This is mainly for particularly you wanted to break down at a particular voltage. So this is a special kind of diode which operate at a reverse bias mode, allowing the breakdown to happen at a lower voltage. But we're not going to talk about the mechanism unless you know the band structure, otherwise it will be very hard to explain. Okay? So just to get a sense, as there are two types of breakdown. Typical devices, if you don't want it to break down, it would then subject to avalanche breakdown. For Zener breakdown, it's typically at a lower level, something like this. You would then have a diode which would have a lower VBD. And this is caused by you simply raise the doping PN junction so that you have sharper angles, sharper triangles. It will then allow you to lower the breakdown voltage, but the mechanism will be a different mechanism. Okay? Good. So once we have some basic understanding, so what you need to know in reverse, let me emphasize once again, 3 key parameters. One is that it's not conducting, basically having a very low current. And then the other key parameter is that it has a junction capacitance which reduces when increased voltage. And then the last thing is that the key parameter you want to know is its breakdown. How much can it sustain? So typically what we want to know is that what is the maximum voltage I can apply on this diode and the circuit it will not break. So breakdown engineer is very important to make sure that the voltage you apply to the circuit is much, much lower than the breakdown limit. Okay? So understanding the limit is very important for a circuit designer, otherwise you will break the house. You'll break the building. So you need to understand what is the maximum a junction can endure. That's the typical limit of your circuit operating voltage. Okay? And then we're going to talk about the second part, which is forward bias. So I'm leaving this plot is because I want to talk about forward bias. So in forward bias, what happened is that in forward bias mode, where VD is larger than 0. So we know that the voltage applied on this barrier will then be reduced because VD is positive, so the height will actually become this, right? Because this is positive. So what happened is that you would then see this. This will actually equals to this, right? So let me just write it down. This will simply be VO minus VD. Now VD is positive. Therefore, you're reducing the barrier. So the first observation is that by applying a positive voltage, we'll then have a reduced barrier. Once you have the reduced barrier, as I said, because my diffusion, this will then allow the current to diffuse because I don't have this barrier between the two. The diffusion force will still be there, but the resistance is lower. Therefore, diffusion will become higher. So you're reducing your drift force, right? I'm reducing my drift force by reducing the barrier. Or you can see from this plot, you're going to get a smaller triangle. Okay? So that would imply that by applying this, the reverse of what happened will occur. The reverse, your depletion region will actually shrunk, and then your junction capacitance, the silk junction capacitance will actually increase. It will actually be higher than CJ0. When you forward bias, you'll be higher than CJ0 if I'm plotting the CJ model. So if I'm doing this, applying CJ as a function of ED, what happened is that, as I said, at 0, this is CJ0. It will look something like this, right? But on the other side, it will then forward. When you forward, you actually increase it. I'm exaggerating. It will look something like this, right? So you actually increase the junction capacitance because you narrow down the distance between the charges. Okay, so that's the qualitative observation, okay, based on this plot. So let's see what happens. What we actually wanted to do is to look at what happened when you forward bias PN junction. So when you forward bias PN junction, if I'm doing this plot, there will still be some depletion in here. So it will be a narrower depletion. So there will be like a single layer. So we know that the depletion region actually shrunk. So I'll still have depletion region, but it's narrower. This is x equals to 0. So if I'm plotting the electron, I want to use. Okay, this is good. So let's say this is the N side. Remember, the other is the P side. So what happened is I start with this. This is NN. And this is NE. MP. Okay? And then on the P side, I would then have, this is PP. On this side, there will be PN. Okay? And I'm adding another notation, which is because we have forward bias and we have equilibrium. So I'm adding a E just to highlight that's the point where equilibrium state remains. So the E will stand for equilibrium. So that's the number we use. So the notation will simply imply the equilibrium state. But when you forward bias it, there's a little change because I'm reducing the potential. So what you think, what we expect is that these electrons would then diffuse into this region, and it will cause electrons to rise. The electron density on the P side, the minority carrier density, right at this junction would then rise a little bit. It's like if I'm reducing the barrier between the two, you will actually see more people coming over at the border, because I'm reducing the resistance, I'm reducing the barrier, so allowing some of them to come over. So you would expect that this will be raised. So then there will be something called the MP during 4 bias. So during 4 bias at this junction, you expect this to rise, and then it will slowly decay. I'm just going to give it a flat line. Okay, so what happened is that these electrons, there will be excess electrons that are coming through higher delta NP. This is the excess minority carriers. So this is more than the balance. So what happened is that at normal, during peace, if there's no wall, there's no refugee coming in. When you 4 bias, you reduce the junction, there's extra forces that forcing people to diffuse. Then you will see more at the border, and then will decay all the way to neutral at the edge, or very far away from the border. Okay, we're going to talk about that a little bit. So the basic idea is that first you need to observe that once I reduce the barrier, I will then allow these carriers to diffuse through the barrier, and then when it comes to the other side, will become excess minority carrier, meaning that exceed. The excess simply means that it would exceed. I should say exceed MPE. Exceed its balance level or equilibrium level. So this will happen on the P side as well, for holes as well. It would then rise a little bit higher, and then you would then have these excess holes. So these are delta Pn excess holes in N-type. It's a minority carrier. So there's excess holes in the N side. So to analyze, so because I'm allowing us to diffuse, then this profile, this slope, we expect this d and dx, and there will be a dp dx, would then lead to diffusion. This will then lead to Jn diffusion. And this two add up will be our current. So your current, you expect the diode current during 4 bias will be area times Jn diffusion plus Jp diffusion. Okay? So now what is being, so we already know that if I can find out the diffusion current density for both carriers, I should be able to find out what is the diode current during 4 bias. So in this key analysis, what is the key parameter you need to know? We want to know this. This. So what governs the d and dx will be the level that's being raised at the border. That would then limit how far or how fast can it diffuse, the profile between. So the difference between these two would then give us how much excess minority carrier is actually into the other side, and then it would then cause our current level. So that would be minority carrier forward, during forward. So let me define this. NPF is the NP at x equals to xn at this particular border. Let me highlight this. So this is P, sorry. This is minus xn, right? I want to, it's probably not. So this is the N side. This is the P side. at x equals to xp, at this junction, passing the depletion region, during 4 bias. VD. So when you apply a 4 bias voltage of VD, what is its level at this particular point? You want to know that. Also, we also want to find out, so that's for electron. For holes, we define P and minority carrier at this border. So this is defined as, I should use definition. This is defined as Pn at x equals to minus xn. And this is also under a 4 bias condition. So let me use consistent colors for my holes. So as this hole, you consider doing 4 bias at this particular junction, what is its levels. So to find out this level, we need to go back to our understanding of built-in potential. If you go back to understanding the built-in potential, I'm just going to write down our previous, the built-in potential. This is the barrier height, which used to counter the potential difference between these 2 points. You don't actually care what happened passing through these 2 points. You're basically looking at these two, right? So VO is defined as VT ln PP Pn. I'm adding an E because this is at equilibrium. VO is at equilibrium. VO just stands for equilibrium. So this is also true for VT ln and the balance between the two on the two sides. Sorry, I made a mistake here. It's P. Okay? It's good? Remember, the point of having this built-in potential is to counter the difference in carrier concentration, diffusion force. This is counter diffusion force. So this should be true. So if I'm reducing the barrier, I'm rewriting, my barrier is being reduced by VD. So what happened is that this will be VT. If I'm only looking at the holes, it will be PP. This still, on this side, will still be PP. But on the other side, it will be PF. I want to highlight this point again. Is that, where's my other, I have this. Because I'm 4 biasing, so it's being raised by how much would depend on the 4 bias voltage apply. So this will be my equation 1. This is my base. This will be my equation 2. So we're going to do some manipulation of equations for us to get P. So what we basically, remember all the exercise, what we actually want is this. You want to find out this, right? What is the excess minority carrier density at this particular point? How much you raise your minority carrier concentration. So using these two equations, we want to get PPF as a function of other or predetermined parameters. So what I'm doing is I'm going to do 1 minus 2. So if I'm 1 minus 2, on the left side it will be VD. On the right side it will be ln. Let me make sure that I get it. If I'm doing holes, I'm just going to use the equation of holes. PNE times, I'm going to reverse that PPF. PE. Okay? Right, if this minus this, I'm just reversing the ratio inside natural log, right? So then I'm getting rid of this. And then my equation will become Ln So this will then give us a very important equation we're going to use a lot. It's called the law of junction. So then I'm getting, so this will then give me how much does the minority carrier concentration, I made a mistake. Sorry. This is minority carrier. So this is the other side, which is PN. Should be PNF. Sorry about that. So this is PNF. I'm looking at minority. Okay? So let me write it down. So what I'm actually trying to find is PNF. It's not PP, sorry. Just make sure that I didn't make other mistakes. And it should be minority carrier, okay? So what actually the final things we want to find is PNF is this is typically referred to as the law of junction. You can do the same exercise for electrons as well. Minority carrier on the P side, PNF. It's original level, it's balance level. Exponential. So these are typically referred to as law of junction. So what this is implied is that law of junction tells us that when you 4-bias p-n junction, what happens is that you will exponentially raise the minority carrier concentration. Its original balance level, I made a mistake, sorry. This small notation, confusing. Okay? So what you do is that you start with this very, very low minority carrier concentration. It's being increased by this exponential factor, which will be depending on how much does one reduce its barrier height. The lower the barrier, you actually have heightened more significant raise of minority carrier concentration. So it basically implies that how much did you raise from here to here will exponentially depends on the 4-bias p-n junction voltage. Okay? So once we have this finding, we already know this point, the access minority carrier. So then this will be fairly simple. What we actually want is to find out the access minority concentration. This will simply be in during forward minus its background during equilibrium. So then you will get NPE exponential VD minus VT minus 1. That's our access minority concentration. And at this 4-bias location, and then PN, access holds in P region is PNF minus PNE, which is PNE exponential VD minus VT minus 1. Okay? So once we have these access minority concentration, the next thing is how much does it diffuse? So what determine, first of all, if we're trying to find out, if I'm defining this by a triangle, I'm simply just going to use a triangle, but let me explain. So let's say I already know my electron access minority concentration. So if I'm plotting delta N as a function of x. We know that at a particular point, it would then reduce to 0 because it would then return to its normal value. And then it's being raised by a factor of, this is delta np, right? So the slope dn dx will simply be defined by delta n. It's a minus sign, right? Because it's reducing. So delta p np divided by a length. Okay? So let's say if we're assuming that it will reduce to 0 at a characteristic length of, we call it diffusion lens. I should say in real device, if you actually look at the minority carrier concentration in the opposite side. So if you're looking at excess electron density along x, it will actually be an exponential decay. But in this case, I'm simply going to use the characteristic length. We define this as, this is actually depending on material itself. So Ln is defined as something called a diffusion lens. Is that not actually a straight line? I'm just using a straight line to approximate what happens so that the derivation will be easier. So this can also be, if you look at a hole density, it will be the same. So we know that there's a height. The axis is delta Pn. And the distance it can go, the furthest for a hole, is the hole diffusion lens. So this is referred to as the hole minority carrier diffusion lens. And this is the electron diffusion lens. I want to mention the diffusion lens only stands for minority carriers. So sometimes you can look this up. Ln and Lp are referred to as minority carrier diffusion. As I said, it actually decays with distance, typically referred to exponential decay. It should be exponential decay. I'm just using a straight line to approximate here. It will give you the same results. Okay? So this will be dp dx. So here dp dx, because it's increasing, so it's delta p n ln. So the slope, if you approximate this with a straight line, it will be this. So then I'm just going to borrow 5 minutes to finish up. So we should be able to, once I have the 3 point, I have the height, I have the distance, I already get the basic parameters to get the gradients. Once we have the gradients, we're ready for current. So let me see if I'm using J or using. Okay, I'm just using J. So let's look at two parts, the P diffusion. Remember, for holes, there's a minus sign, so it's a minus Q dP dx. You go back to look at the diffusion current equation. So it will be a minus Q dP dx. It will be delta Pn divided by Ln. Okay? So we actually get a minus sign because the holes are diffusing in this direction. The holes are diffusing, sorry. The holes are diffusing the current, so the current direction is the same as hole correction. The current direction is the same as hole correction because it's positive charge. So this can be written, the reason for this minus sign is because it's moving in minus x direction. Okay? So this will be, according to that plot, is PNE exponential. I'm simply inserting that into my equation. Okay? And I could also write the electron current. It will be Q dn. Let me start with QDN. QDN dn dx. And we know that by using this, there will be a minus sign dn ln exponential Vd minus Vt minus 1. The minus sign is coming is because of this decreasing density, decreasing gradients. Because my gradient is negative, so you simply insert that, getting the number. So finally, let me, I missed something here, sorry. There's this MPE exponential. Okay? So what we wanted to do is actually sum it up. So finally, let me sum up the overall current. So if you're trying to sum that up, my total current, once again, will be A Jm plus Jp. And because the current direction, I'm just going to get the current direction out of the way. So it's minus x. We know that it's moving from N to P. So this is from, if you're defining the current from P to N, then the minus sign will just come off. So you can get rid of this minus sign. So the net current density will then depend on Q dn ln MPE plus Q dp LP PNE. And then exponential. Okay? So all of them will then, there will be an A, sorry. So if I'm defining this direction, I'm just going to get rid of this minus sign. So your total current will then depend on all this. This will depend on device structure, right? Everything inside will depend on device structure. The rest term will depend on voltage. So it can be summed up as a constant, which will be depending on doping concentrations, cross-sectional area, that sort of things, material, and then finally exponential. All of these will be lumped into a device parameter which called IS. And then you will see the voltage dependency, exponential voltage dependency when device is operating in 4-bias version. Okay? So let's take a break for 10, and we'll come back to discuss a little bit more on this current behavior. Okay, let's continue our discussion on the 4-bias PN junction current. So we already know that we're lumping all the device structure parameters, which is actually defined by the dial. So if I have a dial looking something like this, So let's say if this is the P side, this is the N side. I want to emphasize once again, why do I take away the minus sign in the derivation? Because if we're defining current flowing in this direction as positive, this is ID. So this is actually defined as the minus x direction. If this is the x direction. At our beginning, we're defining x positive on that side. And because current, the minus sign is positive, so I take out the minus sign. So the diode current is positive from P to N. Okay? So we lump it all into this IS current, IS. And then you look at these parameters. One is that it's cross-sectional area. So this is the cross-sectional area. It's device structure. LN, LP are material parameters. So you can actually look it up in material parameters. For silicon at a certain doping, it's a doping-related parameter. And then finally, you look at this. So we're gonna do something with these. Get my equation. So what is the? Remember what is? I want to emphasize. This stands for equilibrium. Thermal equilibrium. So what is the minority carrier concentration? NP at equilibrium is actually Ni squared divided by the minority carrier concentration at the P side. Sorry. This is at the P side. Minority carrier concentration at the P side. So this is the same thing as for P, Ne. It's minority carrier concentration at the N side. Okay? In the opposite side, what is minority carrier concentration? So you simply put them into this equation, then my IS will be proportional to cross-sectional area, and also Q, and I am taking out all the common parameters, and then it will depend on two important things, Dn, Na, Ln, plus dP, Nd, okay? So that is to say, if my doping concentration, this is Nd, this is Na. If I'm doping this with a certain level of dopant, so these parameters are known. So once these devices are made, the doping concentrations are known. These are fixed. And these diffusion constant, these are constant. And cross-sectional area. So once you have all these made, then this will be a constant parameter. So this is referred to as a diode parameter, IS. So if you actually have a device which is being made, for example, if you're actually planning on making a device, for example, in integrated circuit technology, what's typically being done is that I would then have, if I'm looking at the cross-sectional view, it will look something like this. I will start with the, for example, a ND, let's say this is the N substrate. And then I will do some counter-doping, right? So this will be Na. So then if I do a contact here, assuming that the contact is right, then I have P-N structure. If I'm looking at the top, it will look something like this. This will be my substrate region. And then This will be my diode area. AD stands for diode. So AD will be the A we use in that parameters. So you simply define a diode area. It's defined by the P region. So this is the P region. This is the N region. And on the top, you make contacts. So if you look at layouts, what they do is the contact looks something like this. I make a contact. And this will be the same as a diode. Contact. This is the contact. Okay? I don't know if I can. So these two contacts will be here and here. The middle contact will give you the P. The outer contact will give you the N. This is a very poor layout. I'm just saying that this is just a typical, how do you actually make a PN junction in devices. And I want to mention just to make sure that I didn't make a mistake. In real practice, what happened is that you actually see this type of. If you're actually making a real device, just make sure that you have these two underneath. This is just to make sure that the metal to semiconductor contacts are good. So just to make sure that you have a good. The structure is to make good contacts. In case you're wondering, but I'm just trying to make sure that you know that it's the real cross-section should look like this. Otherwise, you won't be able to get the real characteristic of a junction. So this is just to ensure a good contact. So you actually have heavily doped structure under metal to make sure that you're making a good contact. But if you look at the top, it will look something like this. So if you're a designer, I'm just trying to emphasize is that the doping concentration as we use. So for the equation you're using for IS, the ND will equals to ND. The NA, let's just use NA prime. In that equation, it will simply be N counter doping, remember? So ND. So you have to use these into that equation to get your IS. IS. In the IS parameter, you need these two. And then the area will be, the parameter we use area, will be defined by the top view, will be the AD. Whatever top area you use, the diode area, you use that to get your IS. You could actually get that. But I want to emphasize once again is that if you're a designer, what I mean by designer is that all the process, these parameters are fixed by technology. These are fixed. That is to say, if you're using, for example, if you're using certain foundry and they have a certain technology, these parameters are fixed. How much do they dope? They will not change for designer. The only latitude or the only flexibility for designer is to change this. So this is called the technology parameters. So these two are technology based. And this is referred to as the design parameter. So you could actually design your area to manipulate IS by changing the diode area. Okay? So this is one of the limits of having this type of, we call, typically referred to as a bulk devices because the current is flowing through the substrate. So these type of device, you only have one dimension, design parameter, one parameter to design your IS. But if we look at two-dimensional devices such as MOSFETs, you then have two-dimensional freedoms for designers. So there's different levels of flexibility in your circuit or device manipulation of device characteristic. In this case, you only have one. You can only define whether it's a larger device or a smaller device. And this is also true for bipolar junction transistor. It's only defined by one parameters in designer's point of view. Okay? I hope I made myself clear. What else do I want to talk about? Okay. So what is the name of IS? I want to mention this a little bit. So if I'm drawing ID, VD, so now we can actually have the ultimate plot of this current. This current equation will look something like this. This is forward bias, exponential increase, and it's supposed to be, and then it might break down. So this is the breakdown. So if I give you a dial, you can just go buy a discrete device and just do the sweep. You just sweep the dial. So this is very simple setup. You can actually do it on your own. Do a power supply and sweep the voltage and then measure the current. So we measure the current through the dial, and you should be able to get the typical plot. And I want to mention this very, very important concept is that, as we mentioned a little bit beforehand, is that PN junction is actually the core of integrated circuits. So anytime if you're making your own device, anytime my students make their own device, or if you tape out your devices, tape out your circuit, asking for example, the foundry company to make these devices for you. If you're not sure if you're not sure whether your layout's wrong, if you made a mistake, or in your own process of devices, if there's a problem with your process, one of the key parameters we ask every time if I ask the student to debug, this is the critical or the typical characteristic. The first thing we want to see is that if you see this characteristic, do you actually see this? This is very, very unique and typical for debugging. If you don't know what happened, if maybe you misplaced your wire, the key thing is to see whether you see the diode characteristic in your circuit or in your device. Okay, so that's the key. So anytime you see this forward and reverse characteristic show up, that means that you actually make something right. At least this particular structure is correct. Okay. So the other thing is that if you actually look at, if I'm following this equation, this part should follow ID, should follow exponential VD minus VT minus 1. Okay? And this equation does not only work in forward bias, it also work in reverse bias, because law of junction actually work for reverse bias as well. So you actually see that it will extend all the way before breakdown. This equation still holds. So what happened is that if VD is smaller than VT, you expect to see a current which is sorry. I made a mistake. The current equation ID is here. ID equals to IS exponential. So IS exponential VT minus 1. So if your reverse voltage, I should say a minus, this is not a good phrase. Let me rephrase it. If my minus reverse voltage is much, much larger than VT, so this is actually positive sign, okay, minus reverse voltage. This is a problem with minus sign. So if you're at this region where your reverse bias, or this is, if you want to use the positive, this VR, is much, much larger than, your reverse bias is much, much larger than VT. Remember, VT is only how much? Yes, this is only 26 millivolt. So if I'm applying, for example, a -1 volt, it will be much larger. It will fulfill this. And this will be approximately, what? You don't see this, and then it will be -IS. So IS, if you actually see the textbook or in a lot of definition, IS is typically referred to as the reverse bias saturation current. This parameter is typically referred to as the reverse bias saturation current. Because under reverse bias, you actually see a -IS. So this is typical. If you want to look at the leakage current, you can simply use that as your functional equation. Okay? So let me, before we move on to the last part of chapter 2, which is the modeling of device, I wanted to just make a brief summary as to what we have already talked about on PN junction. So first of all, there's 3 conditions where zero bias is VD equals to 0, equilibrium. VD is reverse, and VD is positive. So if you look at the device, it will look something like this. So you would then have typical depletion N side, P side. We'll then have, let me just draw 2 layers. And there is depletion region, just a typical depletion region. And what is the key? So this will be QNA positive. This is minus QND. Sorry. I made a mistake. Let me highlight it. This is donor acceptor. So this is QND. P side is acceptor, N side is donor. Okay? So important things you need to know is that its built-in potential is to counter this. Once again, counter the majority carrier concentration and minority. And then MP. If you want to be more precise, I'm adding the equilibrium state. So because this is equilibrium state, so it's majority, minority, PP. And then it equals to Ln, Ni, Na, Nd. So once you have the fixed doping, you will then have a fixed counter force, built-in potential. The higher the doping concentration, you need a larger, there's a greater difference between the 2 doping concentration, carrier concentration. Therefore, you need a higher counter force. So when we're applying a reverse bias, so if we're defining voltage here, this is VA, VD. So if I'm applying a reverse bias, what happens is that you would then experience a widen of depletion. So you actually see this. Okay, you see a widened depletion, and then this is still QNA, and the doping concentration or the density does not change. But one of the key things I want to mention, it's also true for any condition, is that there's a depletion width, Xn. xp. In any condition, qn dxn plus qna xp. As always true, charge neutrality has to hold in depletion, forward, reverse, all three conditions. So the ratio between depletion region in either is forward, reverse, any type, it has to hold. So the ratio always hold. Ratio meaning that the depletion width ratio. If my doping level, for example, if my doping level is the same, meaning that my width are always the same. In nx equals to np if their doping concentration is the same. If there's differ by 10 times, so the ratio will be inverse by 10 times. So it has always hold in all three conditions. And then in this case, it will be Cj. You only need to consider as a parallel plate capacitance. I believe the textbooks define VR as negative, therefore there's a minus sign. Or if I want to write it, if I don't want to change the sign, it will be something like this. Okay, so if you don't want to change the sign of your voltage, then this will be VD. There's a minus sign. If you're using VD instead of VR, because I'm reversing the direction, therefore, here I define. I just want to make sure this here I define VR as minus VD in reverse bias, just to make the number positive so that it's easier to understand. But if you're not inverting that, then you need to keep the minus sign in front. Okay? And lastly, we talked today about 4 bias PN junction. So during 4 bias PN junction is that you reduce the barrier, the triangle, remember? The triangle is reduced, the barrier is reduced as well. So we get a narrow depletion region. This still holds. I want to mention all three conditions. Charge neutrality has to hold. And what happened is that I would then have holes, access holes here, delta Pn. And I will also have access electron going to the other side. So this would then lead to electron diffusion, hole diffusion, right? Electron moves in this direction, and therefore you get a net current going from N to P. Okay? So I'm having, if I'm drawing a diode, the diode is this direction, right? So currents flowing from P to N. So during this mode, 4 bias, IS exponential VD okay? So that's the current voltage relationship you need to follow. So in a PN junction, what are its key parameters? One is, let me highlight. Building potential is given by once these doping concentrations are fixed. And then CJ0 is typically a device parameter that will be given to you. And then finally, reverse bias saturation current. So these are the parameters that will typically be given to you in a model file, device model file. So once we already know these equations, let's take a look at some examples just to get a sense as to what are the typical current levels and what does this current equation mean. So I'm just going to go through a simple example. let's say for a diode with, so these are device parameters, as I said, device parameter will be given to you. These current levels are typically fairly low, 10 to the minus 17th. So I ask you to find the diode current. If I'm forward biasing, I'm applying a diode, a slight forward biasing voltage, about 0.3 volts. And then if I'm applying a strong forward biasing voltage, let's say I'm rising this to 1 volt, and C, you should be able to determine these levels. So this is fairly simple. What you do is just plug it into this equation. We already know that this is at room temp. So just to emphasize, this is at 300 degree K at room temp. So for problem 8, your IS, your ID will simply be 10 to the 17th exponential 300 millivolt, 26 millivolt. And this will raise your current a little bit because it's not forward biasing enough. It's a little bit it's lower than built-in potentials, therefore it's significant. You're not flattening out the built-in potential. So what happened is that this will be about minus 10 to the, that's 1 pico, about 1 picoamp. Okay? So if I'm applying a voltage of 10 to the 17th exponential, let's say 1,000, 26 millivolt. This will then give me some current level about 0.5 amp. So this is very large. If you're talking about integrated circuit, this is fairly large, close to 500 milliamp. So it's probably the upper bound of how your circuit can survive. So when you apply a very forward bias condition, this will typically be what happens. And if I'm applying a minus negative 5, my ID will simply be minus IS, which will be 10 to the minus 17th. Okay? So if I have these parameters, I can actually do a drawing of my plot. So if I'm drawing in a linear scale, this is the tricky part. So if I'm drawing this thing, if you can do the exercise on your own, just use a spreadsheet, Excel thing, to draw this. Just draw this equation, plotting the numbers, right? And then just draw the figure. I draw the IV, the curve. It will look something like this. You actually see something similar to this. If I'm drawing a linear scale, I want to make sure. So this is a linear scale. It will look something like this. Okay? So you will actually barely see anything under something we call a VD on. So if you look at, you can barely see some current. We define something called a VD on. So if it's lower than VD on, you essentially see very limited amount of current. If I'm highlighting this, this will be, let's say this is a 0.3 volt. It's almost 0 if you're looking at in a linear scale. So if this is VD, this is ID. Right? So what happened is that the turning point we call VD on will highly depend on the scale. What do I mean by this is that if you can do the exercise on your own. If your scale is in picoamp, your VD on will be somewhere around 0.3. If your scale is in milliamp, microamp to milliamp, you will see this around maybe 0.7 volt. So what happened is that it would depend on what would you think as a operational current level in typical circuits. So you want to draw your plots in the relevancy of your circuit level. So typically ID will be ranging from maybe 10 microamp to milliamp range. So if I'm drawing this in, let's say, in a scale, let's say this is 0.5 milliamp, this is 1 milliamp, 1.5 milliamp. So you can do the exercise on your own. You will find out that this voltage median will be somewhere around 0.7 to 0.82. Okay? So it would depend on what is your operating range. What is the operating range of your circuits? If your operating range, the current level you're dealing with is somewhere around here, we typically set our, you will actually see your turning point somewhere around here. Okay, so in exponential systems, if you're drawing your plot in a linear plot, whatever relevant, the relevancy would then depend on, I mean, I said this is current. Okay, so the relevancy of the turning point will depend on the level of your interest or window of interest of your current level. Okay? So this will then allow us to come to our discussion to how to model this device. The third part of this discussion is then, once we have this diode current equation, we basically have two distinctive operating regions. And one region is that it's turning on, exponentially explode. If you want to have a precise model, so let's look at the diode model. I don't know if I think this is probably the first time we deal with something called a device model. The problem with device model is that you will see that we actually already have a model which pretty well, where's my current equation? Pretty well defining our current and voltage relationship. But it depends on what you're actually dealing with. If I'm looking at a very complicated circuit, for example, I have 10 or 20 diodes in the circuit, I don't actually want to know precisely what is current level. I just wanted to know whether this diode is on or off if I have a complicated circuit. So I wanted to have a simple model for me to just to get a sense as to what the overall operation of the circuit. So you start with the simplest model, or if you're looking at this plot, this IV plot, if you go all the way to the back, and then you look at it with the quinted, your eyes are sort of not opening enough. So you barely see the broader sense of this device. Then we use something called the most rough model, I should say, the ideal diode model. What do I mean by ideal model is that I don't actually want to know how much it takes to turn on. I just want to know whether it's on or off. So the ideal diode model looks something like this. It has an equivalency to a circuit. So it has two modes. If the voltage is larger than 1, larger than 0, we said that, I should use the smaller than 0. I should start with smaller than 0. If your voltage is smaller than 0, we assume that it's off. It's in the off mode, therefore we assume that ID is 0. So you view this as an open circuit. Okay? And B is that when your voltage is larger than 1, we assume that it's on. I don't actually care what is the current, because the current will then be determined. In a short circuit, what determines the current? If the device is short, what determines the current? The external circuit determined. Okay, so that what happened is that we assume that it's a short. So in the circuit point of view, we're assuming that there's no voltage across, or it can sustain whatever amount of current. So this is the type of model which will only allow you to determine whether it's on or off. So you only want to get a sort of like a gist of what the circuit looks like. You don't actually want it to go into detail. You just want to know whether it's on or off. And how does it affect the general scope of the circuit operation. So this is called the ideal model. We don't use that too often, only when the circuit is really, really large, or you just want to get a sense. For example, you have 100 diodes. Just want to know which part is on or is off, and how did it work. Okay, so the second model we use fairly frequent is called the constant voltage model. This is also a little bit confusing, but I'm just gonna use this a lot. So constant voltage model is that aside from just giving an on and off, I'm addressing that you actually need to apply a certain amount of forward bias in order for this device to turn on to get a significant amount of current. So then, aside from having the short or open, so the diode will then be modeled to also 2 points. So I'm just expanding my cutting point to a parameter called VD-on. So instead of having a exponential current model which give you an IS, I'm just going to give you a VD-on. So for example, if you're using this equation, I give you an IS, and then you do the plot. And then you size it to the range where your circuit would operate, and then you can get something called a VD-on. You can actually extract something called a VD-on, where it looks like your turning point. So we're doing the transition based on our operating region. So then in constant voltage model, you would then have one parameter, which is VD-on. This can be determined by the current level. As I said, you set your current level, and then IS. So I give you an IS, you use the exponential model, you do the plot, you set a operating current level, and then you extract where you think the on current, where significant amount of current. What I mean by significant is the current level raised to a level which is comparable to the level of interest of current levels. So the scale is very important. So as I said, typically VD-on will be 0.7 or 0.8. It's being extracted by that plot. Okay, so once we have this, then we define this more carefully. So if VD is smaller than VD-on, so if it has not exceeded the threshold, we are assuming that it's in, we call it the same as off mode. And then we're assuming that the current is essentially 0. We view it in a circuit as an open circuit. Okay? So there's basically no current flowing in a reverse bias diode. And of course, if it's higher, equal, and larger than VD-on, we're assuming that it turns on. It's an on mode, and the model to view this will be P. Oh, sorry. Which side? Okay, this is P, and I'm flipping the side, so. So what do you substitute this component when it's turned on? When it meets the requirement of exceeding VD-on, we're assuming that the diode would then take up a voltage drop of VD-on. So this is called a constant voltage model. The current, if I'm drawing its current voltage equation plot, it will look something like this. For the ideal model, the IDVD will look this, 0, 1. Okay, it will look something like this. If I'm doing the second one, this is the ideal. So if I'm using the constant voltage model, yellow. It will look something like this. it will require a voltage, and then afterwards will be mostly like a short, it will be a straight line to the top, meaning that its voltage, its current level will be undetermined. It will be determined by external circuits. Once again, it will not stand alone anytime. You will then have external circuit, which would then give you, it will not explode to infinity. Because when we first introduced this type of model, students are very confused because you don't actually know the current level. But how do you determine the current level of a voltage, I should say a voltage source? It will determine by external circuits. So whatever external circuit would then give you your final current level. Okay, and finally, if you're doing SPICE simulation, or you can do some hand calculation, because the current equation is barely, it's not that complicated. So the third is for, let me do it here, called a SPICE. SPICE for circuit simulation. So what you use in SPICE model is basically ID equals to IS exponential VD minus VT minus 1. And this is being used in, you simply use a voltage control current source. And its current equation, voltage control current source. And simply use that to for SPICE. In SPICE, what they do is just use this type of equation, nonlinear equation. You can actually find out your current level at each particular location, situation. Okay? This good? I don't know. I don't think I have time. We can come back to do some example on Thursdays. But just to give you a sense as to the use of model, or this is actually the most, I think, the most tricky part, or the hardest part for beginners to get a sense as to what should be done. So I often refer this to as the zooming problem. If you're looking at a view, if you want to look at the big picture, what you want to do is that you back off, and then use a very, very rough sense of how these elements works, and then get a larger picture. That's when you want to use models similar to the ideal diode model or constant voltage models, just to give you a sense as to the basic function. You don't want to know the detail. But anytime when detail required, you want to zoom in. So you want to zoom, you want to get a sense as to learn how to zoom out and zoom in. And this is very hard. I'm not expecting the beginner, your first time students to be able to zoom in and out appropriately. But this is just to give you a sense as to how you, this is I think the basic training where you accumulate a sense as to when to zoom in and when to zoom out. Otherwise, it's very hard to get the bigger picture of how the circuit works. So we're going to encounter this problem along the way, anytime, especially when we deal with circuit analysis, because we're going to enter the circuit part pretty soon. So when we enter the circuit parts, you will then see, sometimes I mentioned that, oh, if you look into this direction, you see what? But you don't actually see it. You have to see it when you zoom in and out frequently, and then you get a sense as to how these things works. But that would come in with experience. So if you don't get it the first time, don't worry about it. You can always go back to the most sophisticated model. The problem with this is that it will be very time consuming, and then it will sometimes you lose sight of the bigger picture. So learning to jump around these models. These are all models, it's just the precision level is different. So then when do we zoom in, when do we zoom out? It's a very hard, I cannot give you a precise answer, just to tell you that there's different models we're going to use, and then you will see that we use different models at different scenarios. Okay? So let me just stop here, and then we'll come back on Thursday and go through a few examples so you get a better sense as to how people use these models and what are the discrepancy between the accurate, more accurate model or less accurate model. You want to tolerate, to get a sense of how much you can tolerate the error.